So we go on with this mini course about the isoperimetric problem on Riemannian manifolds. So last time we just introduced the perimeter functional, the problem, and we discussed examples and so on. And today and tomorrow we will see a couple of selected topics on the isoperimetric problem. So the topic of today is called the differential isoperimetric inequalities for the isoperimetric profile. And this is the first time that it will play a role, a lower bound on the curvature, and precisely on the Ricci curvature. So let me, even if this already appeared in the conference, let me remind what I mean by lower bound on the Ricci curvature. So I will start with a remark. Always, as always, the setting is the one of a smooth Riemannian manifold, Mg, dimension capital N, and so on, complete, usually non-compact. And I just want to remind to you what is the so-called Bochner identity. If I have my complete manifold, I take, for example, a smooth function over the manifold, then there holds the Bochner identity, which is this differential identity, 1/2 Laplacian gradient square equal to Hessian squared plus scalar product between gradient delta f, gradient f, plus Ricci applied to gradient f. So if you have never seen this identity, so what's going on here is the following. Forget about the last term. If you try to compute, for example, 1/2 Laplacian of the gradient square of a function on Rn, you just get this differential identity. There's nothing, I mean, deep behind. If instead you are on a Riemannian manifold, even if you don't know the geometric definition of Ricci curvature, the fact is that this identity is true again, but with, if you want, with a correction term that is a tensor, it's an operator, Ricci, applied here 2 times to the gradient of f. So this is a very analytical definition of the Ricci curvature. If you want, it is the operator you need to plug in here to make this identity hold true. So this is the Bochner identity. And here comes the definition that I can give through the Bochner identity, the definition of what I mean by lower bound on the Ricci curvature. So here it is inequality, there is a definition. I say that Ricci is greater or equal than k, where k is a number, possibly negative, if as an operator, if you want, as an operator, in the sense of matrices, if you want, is bounded below by this constant. So the right-hand side is greater or equal than Hessian squared plus gradient f plus k gradient f squared, right? So if you want, it's greater or equal than k times identity, if you want, k times the metric. And okay, and actually, if you are on the other hand, right, on a smooth Riemannian manifold, if you assume this inequality to hold true for any smooth function, you recover the classical. You recover the fact that the Ricci curvature is bounded below by k in the classical sense, if you know what it means. So this is the definition, and this inequality encodes a lot of meaning, and it will be very useful in a few minutes. So in a few minutes, we will work on manifolds with Ricci bounded below by a constant k. And okay, now we move on to the true topic of today. So the title of today is differential inequality. Differential inequalities on the isoperimetric profile. Profile. Okay, remember we defined in the last lecture the isoperimetric profile. The isoperimetric profile of a manifold M at a volume V is a function of one variable, and for any V that is a positive number, a volume, an admissible volume, V between 0 and the total measure of M, this is the infimum of the problem. So the infimum of perimeter of E among sets having measure equal to V. That's the definition we gave last time. And if you remember, we computed, for example, the isoperimetric profile of Rn, right? Because we proved that balls are isoperimetric sets, and we proved, in particular, that the isoperimetric profile of Rn is n omega n power, so a constant, a positive constant, times volume to the power n minus 1 over n. So in particular, this is a strictly concave strictly concave function of one variable, I over n, and it looks like that, right, with respect to the volume V. And so a more or less spontaneous question is the following. One possible question among those that you can ask about the isoperimetric problem is, what can you say about the isoperimetric profile, about its value, about its behavior as a function of one variable? So one can ask, just like Rn, is it possible to say that on another manifold, in some sense related to Rn or related to a model manifold, can I say something about the behavior as a function of one variable of the isoperimetric profile? And in particular, can I say something about the concavity of that isoperimetric profile function? And the answer is yes. And it is precisely the claim stated in the next theorem. That is the main theorem of today. So I'm going to call it theorem 1, but just because there will be other theorems later, but this will be the main one. And it says the following. Take again your smooth complete Riemannian manifold and assume, and we have two assumptions. The first one is a lower bound on the Ricci curvature in the sense we said above, right? And then I ask for another condition that is the following. I ask that the infimum over the points in the manifold of the volume of ball of radius 1 is positive. Now, it maybe it appears as a strange assumption, but I will discuss about this later. In any case, it is precisely saying that balls of radius 1, independently of the radius of the center, they contain at least a certain amount of volume, right? So two assumptions. Then I can say the following: if we define psi of v to be the function isoperimetric profile raised to the power n over n minus 1, so precisely the opposite power with respect to the spontaneous one in Rn, then this psi satisfies the following differential inequality. Psi second derivative is less than or equal than minus kn over n minus 1 psi 2 minus n over n, in the sense, if you want, as distributions on the interval 0 volume of n. Okay, so this is the main statement, and as I said, it is a statement about the concavity property of the isoperimetric profile function, or if you want, of the function psi, that is the profile raised to this power. In particular, for example, when k is equal to 0, so I am in a non-negative Ricci case, here k is 0, and so the inequality exactly becomes psi second derivative less than or equal than 0, which is exactly saying that psi is concave, exactly as it happens on Rn. In fact, if you raise the isoperimetric profile of Rn to this power, the profile of Rn becomes a linear function. So precisely in that case, the second derivative is 0. And this also tells us that this inequality is sharp, right? Because equality is achieved in the case of Rn. Actually, analogously, if you require the Ricci to be positive or bounded by a negative constant, then again, you can see that the inequality is sharp if you compute it on the model with constant sectional curvature, so the correct sphere or the correct hyperbolic space. So in any case, it is something telling me an upper bound on the second derivative. So it is telling me that in a sense, this isoperimetric profile is concave, has some concavity property. And just a final comment, I said this holds in the sense of distribution, so it means that if you multiply by a test function on both sides, a non-negative test function on both sides, and you imagine to integrate by parts twice, then you get the actual meaning of the inequality. I will not focus on the regularity of the isoperimetric profile. By the way, it is not a smooth function, so it is not possible to take a second derivative in a classical sense here. But okay, I will forget about the regularity in the rest of the lecture today. So this is the meaning of the claim, at least. And by the way, let me mention that this theorem has quite a history, because also the proof we'll present below contains ideas that go back actually to Gromov, and precisely to a work of Gromov of 1980. When he proved the so-called Levy-Gromov, today we call it as the Levy-Gromov isoperimetric inequality. That is something that we will see tomorrow, actually. So there are already some ideas coming from him. And then the first instance of this inequality was proved more or less in the same years by Bavard, Pansou in 86, and more or less in the same years by Gallot, 88. Let's say on compact manifolds. This, if you want, on compact manifolds. On compact manifolds. And assuming that isoperimetric sets are smooth. When I say smooth, I mean that the boundary is a smooth submanifold, compact smooth submanifold. Then another proof was given by Bale in his PhD thesis in 2003, actually. And Bale realized that the optimal regularity of isoperimetric sets on Riemannian manifold that I did not discuss was enough. So he removed, if you want, he removed additional assumptions on the smoothness of isoperimetric sets, but he always needs existence of isoperimetric sets to prove this theorem, existence of isoperimetric sets as an additional assumption. And the first time up to my knowledge where this inequality was proved without assuming existence of isoperimetric sets was in a more recent paper by Mondino and Nardulli in 2016, where they deal with manifolds having these two assumptions plus some assumptions at infinity, so plus some asymptotic assumptions in the case of non-compact manifolds, non-compact manifolds. And so to get these final statements where even these asymptotic assumptions are removed, so the fact that the statement holds only assuming these assumptions, it is a result obtained by myself in collaboration with Antonelli, Pasqualetto, and Semola, appeared last year. So the very final statement that I stated is contained in this last work, and actually, if you want to know, it is proved on a higher grade, if you want, in a more general situation, the one of a certain class of metric measure spaces that will appear later in this talk anyway. So okay, eventually you have this statement. And just a couple of remarks on the assumptions again. So a couple of remarks on the assumptions. Well, of course, whenever you have a compact manifold, then automatically you have a lower bound on the Ricci curvature and a lower bound on the infimum of the volume of the ball, just by continuity, right? So this is why I told you since from the last lecture that the difficult part, in a sense, appears when you look at a non-compact manifold. So the first thing, if you have a compact manifold, not only the assumptions are satisfied, but also, as we discussed last time, when you have a compact manifold, you also have existence of isoperimetric sets for any admissible volume. This is also true, while it is not true in the non-compact case, right? And as you may have understood when I discussed the literature, the existence of isoperimetric sets is a crucial point in some proofs, right? Because, as we will see, to derive the isoperimetric, the differential inequalities, we will actually work on variation over an isoperimetric set to get information on the isoperimetric profile. So that's why existence of isoperimetric sets was so important, and it will be important in a certain sense. But nevertheless, we will obtain the inequality without assuming existence of isoperimetric sets. So from now on, basically, we will be interested in the non-compact case. Then in the non-compact case, it is meaningful, in particular, the lower bound on Ricci curvature for sure, but it is meaningful the second assumption, right? The fact the infimum of volume of unit balls is strictly positive. So I want just to give you an idea of what this means. So basically, this rules out this situation, the fact that you have that your manifold has a cuspidal end, right? If you have a cuspidal end, then if you take balls of radius 1, okay, sorry, can you hear me again? Yeah, sorry, I lost the connection for a while.
Yeah, we can hear you now.
Okay, so I don't know at which point it interrupted, but
that condition rules out
exactly this picture, right? So the fact that a manifold has a cuspidal end, because otherwise, if you take a ball of radius 1 with center away along this cuspidal end, the volume inside that ball is going to 0, right? So this rules out this fact. So it is kind of a technical assumption we will need later during the proof if you want, as a technical assumption. But the last comment I want to make is that it is actually an assumption also necessary in a certain sense. So these assumptions, in a sense, is also necessary. But necessary for what? For having a non-trivial problem, a non-trivial isoperimetric problem for, let's say, for having non-trivial problem. What I mean by non-trivial problem, I mean that one can prove the following lemma. For example, under non-negative Ricci, you can prove that actually the fact that infimum of unit ball, of the volume of unit balls, is positive. Oh, let's state in the other way. If the infimum is equal to 0, then this is actually equivalent to the fact that the isoperimetric profile is identically vanishing. So in particular, the infimum of the problem is always 0. You will never have a minimizer, right? So in this sense, the assumption is necessary. It's necessary to have a non-trivial minimization problem. Okay, so of course, this is not obvious. You have to prove it, this equivalence, but it's not too difficult. It is based on the so-called Bishop-Gromov volume comparison. That is something that we will discuss again tomorrow. So this was to give more or less an idea of the proof. And now for the rest of the lecture, I would like to try to give you an idea of the methods that are needed to prove theorem 1, So from now on, we will discuss proof of theorem 1. Okay, so in order to tell you something about the proof, I need to recall you something about isoperimetric sets. So let's keep in mind what we want to prove, but now I make a digression. So I always have my manifold, and let's say that E containing M is isoperimetric, is an isoperimetric set. So it minimizes the perimeter among sets having the same volume. And for sake of simplicity, let's also assume that E is smooth. So the boundary of E is a smooth submanifold. Well, then the first fact that for sure you already know is that the boundary of E has, being a critical point of the perimeter with respect to variation preserving the volume, the boundary of E has constant mean curvature, CMC. And I will denote it by H. So what I mean in a picture is that if this is my set E, okay, and this is the inner unit normal, let's say the mean curvature vector is equal to H nu. So this is my convention on H. And also I am thinking that the value of H is just the sum of the principal curvature, not the arithmetic mean. So this is just to tell you my convention. Anyway, an isoperimetric set has constant mean curvature. I will not prove this, but yeah, for younger people, if you want, you can find more discussion on the book by Chauvel, for example, Riemannian geometry by Chauvel, where you can find also a lot on the isoperimetric problem, actually. So this was the first observation. Now, I want to define an important function that is going to play a crucial role. It is called the signed distance function. Signed distance function. It is the following function. I'm going to call it ds, and it is the signed distance function from, it is understood, from the set E. I am fixing my isoperimetric set from the set E. The signed distance function is just the following: distance at a point x. By the way, it is a function on the manifold into R, and distance at a point x is equal to the distance of x from the boundary of E if x is outside, so in M minus E, if you want, while it is minus distance from the boundary in case x is inside. Okay, so this is the so-called signed distance function. You just change the sign when you are inside E, right? So it's a nice, it is a nice Lipschitz function, and the observation, the remark, is that, of course, the boundary of E is exactly the zero level set of the S, right? It's exactly the zero level set. Also, I will denote, for example, ET to be the sub-level set of ds with respect to the value t. Okay, so in particular, when t is positive, I'm taking a tubular neighborhood that contains E, while when t is negative, I am taking a sort of tubular neighborhood inside, right? It's no longer a tubular neighborhood of the boundary, right? So I'm restricting my set. I believe you can understand it. So ET is going to be the sublevel, while the boundary of E is exactly the zero level set. And now the final observation of this remark, which I leave to you as an exercise if you want, is that the value of the constant mean curvature of the boundary of E is still my isoperimetric set, is exactly the Laplacian of the S. This is a very classical identity, right? When you have the level set of a function, then the Laplacian of that function gives you the mean curvature, right? Also, boundary of E is smooth, so the signed distance function is smooth around the boundary, and I can compute this Laplacian. And now it comes the first theorem, which relates something going on about an isoperimetric set with the lower bound on the curvature. And from now on, but just for sake of simplicity, let me assume that the Ricci is non-negative. You can do everything with the Ricci bounded below by k, but it just becomes more ugly and difficult to write. So just for simplicity, from now on, let's stay in the case when Ricci is greater or equal to 0, okay, from now on. And so the result I wanted to tell you is the following proposition, if you want, proposition. It tells me the following: if Ricci is non-negative and E is my isoperimetric set, smooth as above, with constant mean curvature equal to h number, then I can tell you that the Laplacian of the S is greater or equal than this function, h over 1 plus h n minus 1 ds on E, while the Laplacian of the distance function is less than the same function, 1 plus h over n minus 1 ds on the complement on m minus E closure, in the sense of distributions, as distributions. In a weak sense, in a weakly, if you want, weakly, just weakly. Okay, so what's going on here? It happens the following, right? That I had my isoperimetric set E here with its boundary, that is a CMC. And now, and on the boundary, I knew that the Laplacian of the distance, of the signed distance, is equal to h. Now I'm telling you that this information, that was an information localized on the boundary of the set, propagates on the whole space. And precisely outside of the set, I get this upper bound on the Laplacian. So everywhere I get, in a weak sense, this upper bound. So S distribution means, again, I imagine of putting a Lipschitz function here and integrate once by parts here, then you get the actual meaning of the inequality, right? So outside, I get this inequality in a weak sense. Inside E, I get the opposite inequality, if you want, in a weak sense. So a local information becomes a global information, and here it will enter the information on the lower bound on the Ricci curvature. I try to give you a very rough idea of the proof of this fact, because here is exactly when the Bochner inequality, the Bochner identity, which turns in an inequality thanks to the Ricci bounded below by zero, enters into play. So basically, the idea is, forget about the fact that the sign distance function is not smooth. Forget about it. So the idea is apply Bochner on the sign distance function, pretending that it is smooth. Of course, you need to do everything in the sense, in a weak sense, right? But Bochner on the S. What do I get? I would get the following. I would get 1/2 Laplacian of the gradient squared. But the gradient of the distance is 1, right? It is constant. So I can tell you that this is 0. The Laplacian of 1 is 0. On the other side, I had Hessian squared plus scalar product between gradient of the Laplacian times the gradient. Because here I am using Ricci non-negative. I can go on with this inequality, estimating from below the Hessian by the Cauchy-Schwarz inequality, right? I can put here Laplacian of the distance function squared over n minus 1. Here I'm using Cauchy-Schwarz in order to estimate from below the squared norm of the Hessian, okay? And here it appears n minus 1 and not n, because one eigenvalue of the Hessian of the distance function is 0, right? So I only count n minus 1 non-trivial eigenvalues. Plus, what is here? Here it is exactly, by definition of gradient, if you want, it is the derivative of the Laplacian of the distance function along the direction gradient of the S, right? So it is maybe more common to write it as dr delta ds, where by dr, I am just meaning that I am taking the derivative along a geodesic for the distance function from the boundary, right? So in the picture above, here is a point from the boundary. Here, imagine you have a geodesic realizing the distance from the boundary. So dr is exactly the tangent vector. If you want, dr is exactly the gradient of the S, okay? So I'm taking that kind of derivative. But now you can see it, because now, what do I have? I have actually an ordinary differential inequality, right? An ordinary differential inequality, if you read it. And I have a boundary condition, an initial value. I know this on the boundary of E. And so if you couple an ordinary differential, this ordinary differential inequality with this initial condition, if you want, by comparison, you get estimates on Laplacian of the distance function far from the boundary, and precisely these estimates that I stated above. Okay, so this is a very rough idea, but you can see directly where Ricci non-negative comes into place here. So you have this very beautiful information, but we are interested in a corollary of this proposition, actually. So we are more interested in the following corollary. Corollary, given the above, so previous setting, I can estimate the perimeter of ET. Remember, ET, maybe I write to you again, ET is the sublevel of the sign distance function. I can estimate its perimeter in terms of the perimeter of E. And precisely, perimeter of ET is less than or equal than perimeter of E times 1 plus h n minus 1 t to the power n minus 1 for any t. So, so what's going on here is that, okay, it's, I believe it's clear, but in any case, this is E. For example, this is ET, meaning that the distance here is t. I estimate its perimeter in terms of the perimeter of E and in terms of the mean curvature. This is, by the way, a sort of, if you want to call it a Heinz-Karker comparison inequality. So it's a very classical thing, if you want, in a certain sense. And again, what is the proof of this inequality? I can tell you again the idea. But the idea is very simple, because given the above differential inequalities on the Laplacian, you just need to integrate the inequalities on a suitable tubular neighborhood precisely. Imagine that you want to estimate, imagine that t is positive, for example. Imagine that t is positive, and imagine you want to estimate the perimeter of Et. Then you can integrate over Et minus E, the Laplacian of the distance function. And on one side, you have an estimate on this Laplacian, you have an estimate. On the other side, you can integrate by parts this using the divergence formula, the Gauss-Green theorem, if you want, right? The plus divergence theorem. And when you use the divergence theorem, you will exactly get the difference of the perimeters, perimeter of Et minus perimeter of E on one side, and on the other side, use the inequality that you proved in the previous proposition on the Laplacian on the S of the S. Okay, right. So this is basically the proof. And now we are almost done. You can forget about the previous proposition. We will just need this corollary to actually prove theorem 1. So now I can state proof of theorem 1. But again, in order to show you the proof, I will need to assume something more. So I recall you that I am still assuming Ricci non-negative. I am still assuming, I'm still assuming Ricci non-negative. And if you want, for simplicity, for the time being, for this proof, I will also assume existence of isoperimetric sets. I will assume that they are smooth. Okay, these sets are smooth. And in order to do computation more easily, I will always assume that also the isoperimetric profile as a function of one variable is smooth. So basically what I will show you is basically the original proof of Bavard, Pansou, and Gallot in a certain sense, assuming everything. Then I will try to tell you how to overcome these further assumptions to get actually the final statement. Okay, so how does the proof work? It works as follows. I want to prove the inequality in a pointwise sense at some volume V. So let V be an admissible volume, right? So V between 0 and the measure, the total volume of M. And I want to prove precisely at that volume that the inequality pointwise holds. Around this volume, in a minute, I will consider two functions. One function is the usual isoperimetric profile. I don't know how it looks like, but let's draw it like that, like if we are in a RN. So let's imagine that this is IM. And so here you have IM of V. And since I am assuming existence of isoperimetric sets, I can say let E contained in M be isoperimetric, be an isoperimetric set of that volume. So the measure of V is exactly V. And I will consider the function of one variable that is consider function of one variable sending t to the perimeter of Et. So in the notation above, Et is the sort of tubular neighborhood, right? This kind of flow that emanates from E inside and outside. And I consider the perimeter of Et. So the volume of Et is different. For positive T is bigger, for negative T is smaller. And in particular, of course, you have a trivial inequality. The perimeter of Et is greater or equal than the profile precisely computed at that volume, right? By definition of profile, because it is in the infimum of the perimeter for any volume. So on the same picture, you can imagine that above, okay, I don't know how it looks like, but above my isoperimetric profile, I have the perimeter of Et, right, as a function. And now also you can understand why existence of isoperimetric sets simplifies everything, because in a minute, since I have these two functions touching, in a minute I will differentiate the above function to get information on the function below. But at the point where they touch, I will get information also on the derivatives of IM. So that's the idea. But to do this, I need the existence of isoperimetric set. That's why it was so important in the classical proof. Because once I get an isoperimetric set, I do this argument and I take a variation, right? A variation of the isoperimetric set. I will differentiate eventually the perimeter along this variation. And since the two functions touch, I will get information on derivatives of IM. So now it's only computations. So let's do them. It's quite it's brief. It's brief, but the crucial idea was the one I told you now. So computation, I go below. Computation number 0. Computation number 0 is the simple one, simple observation. So if I take the derivative, for example, of the volume computed at t equal to 0, this is exactly perimeter of E, right? Because if I take the derivative, a variation of the perimeter of ET with respect to this variation, this is exactly mean curvature times perimeter. These are classical formulas you can derive looking at any book. And I can also tell you what is the second derivative of the volume, again at t equal to 0, and this is equal to h perimeter. So these were computation, and maybe a last computation number 0 is the following fact that it is the observation I made above. I am at the volume of ET, if you want, minus I am at the volume V, is less than or equal than the perimeter of ET minus perimeter of V, right? Because these two are equal because E is isoperimetric for volume V, while this is the dumb inequality by definition of the profile as an infimum, right? And but now I wrote it in this way because now dividing by t positive, for example, I can take derivatives, right? I can take derivatives since they are touching, and I deduce, taking derivatives, that the first derivative at the volume V of the profile is equal to h. It's a very classical observation that the derivative of the profile is the mean curvature. So these were computation number 0. But you remember, I am interested in concavity properties of the profile, right? So I am interested in second derivatives. So here are the non-trivial computations, but at this point they will be elementary. So computation number 1 about second derivatives. I want the second derivative of IM. Instead, I compute the second derivative of IM composition with the volume of ET at 0. So what do I get? I get, just by chain rule, I second derivative of V at V times the first derivative of the volume at 0 squared plus I prime at V, second derivative of the volume at t equal to 0, right? Just by chain rule. But now I know from point number 0, I know the values of these derivatives. Here I get IM second derivative times perimeter, right? So times IM squared at the volume V, plus here I would get the second derivative is h times perimeter, but h is the first derivative. So I get first derivative twice, so IM V squared times IM V. And this is the very computation, right? So I just did the second derivative of this composition. And now the second and final computation is to estimate from above, thanks to the upper touching function, to estimate from above the second derivative of this composition, IM ET at t equal to 0. And this is a second derivative, so I can write it as a limit of a second order difference quotient, right? Something like that. I can take the limit as t goes to 0 plus of 1 over t squared, and here I take IM at the volume of ET, so the function computed at t, plus the function computed as minus t, minus twice the function at 0, so in particular at my central volume. And here I use the stupid inequality that the profile is less than the perimeter. So this is less than limit as t goes to 0 plus 1 over t squared perimeter of ET plus perimeter of E minus t minus 2 times perimeter of E, because again, this is an equality, because E is isoperimetric. And finally, I now use the corollary that I told before. I haven't used it yet, right? If you remember the corollary above, I go above just for a while. The corollary above exactly gave me an upper bound on the perimeter of ET, right? An upper bound on the perimeter of ET. And so this is the moment where I apply this upper bound below here in order to estimate these two terms from above. So less than or equal, then what do I get here? If you remember, the estimate was perimeter less than perimeter of E times a function that depends on T. So eventually I can factor out perimeter of E, and I get perimeter of E times the second derivative of that function. The second derivative of the function was 1 plus h over n minus 1 t to the power n minus 1 computed at 0. If you do this computation, remembering that h is actually the first derivative of the profile, you get that this is equal to n minus 2 over n minus 1. It's not really important. I prime v squared im of v. Okay. And now we are actually done. Putting together what we have found. This was greater or equal than the second derivative of this composition, but the second derivative of that composition was actually equal to this other thing that I'm now coloring with yellow. And so eventually I get an upper bound on the second derivative of an upper bound on the second derivative of the profile at the volume V, pointwise. And if you rearrange terms, you actually realize that this is equivalent to the inequality that I stated. So the upper bound on the second derivative of psi, which was I raised to the power n over n minus 1. Okay? So you see that it was actually crucial to have existence of isoperimetric sets if you want to run exactly this very process, right? This very process. And so in the remaining time, I would like to try to tell you how to overcome existence of isoperimetric sets, and so how to get the final statement in the way that I stated. Just a question: can I go on for 10 minutes since we started? I don't remember when we started.
5 more minutes, it's fine.
5 more minutes, okay, thank you. So the final comment is how to overcome, let's go in another page, overcome non-existence. Overcome non-existence of isoperimetric sets. And the idea is to apply the following theorem. It's a theorem that goes under the name of generalized existence, or also asymptotic mass decomposition. Asymptotic mass decomposition. And it is what you do when you don't have existence, right? You find a sort of generalized existence. And this is another theorem with some history. It is ultimately based on the concentration compactness principle of Lyons in the 80s. And the first people trying to realize the following theorem were Ritoré and Rosales in 2004. But the final statement that I will now state is contained in the final paper in collaboration with Antonelli and Nardulli, which is based on previous works by Nardulli, so based on, so after other works by Stefano Nardulli, and another work in collaboration with Antonelli and Fogagnolo. Okay, to tell you the history. And it has the following. Again, take mg as before, Ricci bounded below. I can take Ricci bounded below by k, doesn't matter. And finally, it appears my assumption on the volume of unit balls. I take EI containing M, a minimizing sequence for some volume, so constant volume and perimeter of EI go into the profile at that volume. And I ask what happens. So the statement is going to tell me what happens in general, even if I don't have existence. So remember, in the first lecture, we said that the problem is that maybe for a minimizing sequence, it is convenient to translate, to go away towards infinity. Here I'm, of course, assuming that the manifold is non-compact. In the non-compact case, non-existence was exactly related to the fact that possibly a minimizing sequence goes towards plus infinity. But how does it go to plus infinity? This theorem tries to answer to that question. And I want to draw a picture to tell you the thesis because it's much simpler. Let's say that this is M, and this is my EI, so the minimizing sequence. What it is possible to prove is that the minimizing sequence splits into finitely many pieces. One piece, I will call it EIC, where C stands for converging. The other two pieces, let me call it, for example, there are finitely many, let's say there are two, EI1D and EI2D, where D stands for diverging. And basically, I can identify the part of the mass which remains, which converge on the manifold, and the part of the mass which diverges along the manifold. And maybe one of those can be empty, but the fact is that EIC converge in L1 to a set EC infinity inside M, while the other two pieces go towards infinity. How can I say that they go towards infinity? In the following sense, there exist sequences of points, x1, xi1, and another sequence, xi2, going towards plus infinity, so they escape any compact set, and also they are mutually diverging, so the distance between the two sequences goes to plus infinity. And I can identify some radi that eventually contain EI2D, EI1D, and so on. And so I can tell you that in this sense, this part of the massing goes to plus infinity. Not only, I can use a very useful precompactness theorem, so that I don't have time to discuss now, but just let me mention the name, the Gromov precompactness theorem. To tell you that in a generalized sense, a very weak sense, just under the two assumptions, and for example, here I am strongly using the fact that the infimum of unit balls is strictly positive, I can tell you that locally around, for example, this sequence of points, the manifold is looking more and more similar to a certain metric measure space. This is so it is converging in a certain sense that is called the pointed measure Gromov-Hausdorff sense, to a new space. And since the convergence is very weak, the limit space is not going to be a manifold, but in general, it is only going to be a metric measure space. So locally around the point xi2, for example, my space is looking closer and closer, more and more similar to some singular final space that I can call x2, for example. So x2 together with its distance and the Hausdorff measure related to its distance is a metric measure space, as we just said in this tripole, we call it a metric measure space. And there is a way to say that the mass of the minimizing sequence that entered in this ball is not lost. It is recovered. By a final set here, E infinity 2, that is contained in X2. So in a certain sense, you are sort of compactifying your manifold. The important fact is that all of the final pieces, so EC infinity and E infinity 2 and E infinity 1, all the pieces are isoperimetric, all of them in their ambient. So, for example, E infinity 2 is isoperimetric inside X2. Remember that once we have distance and volume, we can speak about isoperimetric problem, right? As we said in the last lecture. So I can tell that this is isoperimetric. Moreover, the final fact is that this metric measure space is not completely random, but it belongs to the class of so-called RCD-KN spaces that already appeared in the conference. So they are spaces that keep, in a generalized sense, the same lower bound that the manifold had. And now the final identity is this one, and I conclude. Remember, the isoperimetric profile of the manifold at the volume V was the limit of the perimeters. Well, the limit of the perimeters, this is part of the theorem, is actually the sum of the perimeter of all the final pieces you obtained. So this is perimeter of EC infinity plus this finite sum of perimeter over E infinity I of these pieces that were diverging. Let's add a D. Let's add a D. So in a certain sense, even if you hadn't isoperimetric sets in the manifold, so maybe IC infinity was empty, I recover my profile putting together the perimeters of possible limits at infinity. So in a certain sense, this sort of disjoint union of pieces at infinity solves, in a generalized sense, my isoperimetric problem. And so now the goal is perform the same argument we did before on these pieces. So I have at least one, I take enlargements, I do the variations I did before, and I do the computation I did before, and I realized inequalities, differential inequalities, the wanted differential inequalities on the profile. Of course, you have to deal with regularity, a lot to deal with regularity, because these spaces are non-smooth, but this is what is contained in our last work. Okay, sorry very much. Sorry for the overtime. I finished for today. Thank you very much to everyone for the attention.
Thank you. Thank you very much for your talk. So are there any questions?
Hi, Marco. Thank you very much. I want to ask you about this limit set. Do you know if you can, if this is not an isoperimetric set, but is it possible to have a kind of isoperimetric inequality for this set or something like that, even in a weaker sense or something?
Okay, so well, maybe I was very quick, sorry, but these sets at infinity, they are isoperimetric sets inside their ambience. Okay, so they actually minimize the perimeter. They will have some volume, maybe less than the total volume because the mass is splitted, maybe. Mm-hmm. So they will have half of the volume, maybe. But inside their ambient, they are isoperimetric. So compared with any other set with the same volume, they have less perimeter. So they have less perimeter. So for example, you can say something like, so the perimeter of E infinity JD, so is the profile of the space xj at that volume, like this, right? At that volume. So for example, after you have this equality, for example, you realize that you have an isoperimetric inequality, if that was what you were asking, because, for example, the perimeter of these sets, so in a sense, the isoperimetric profile at these spaces at that volume is, for example, less than the profile of the manifold at the original volume V. So this is the first thing that comes to my mind. But anyway, tomorrow we will discuss isoperimetric inequalities, and again we will use, I will show you how to use these generalized existence results to get isoperimetric inequalities on the starting space. Just like now, we want to prove differential inequalities for the profile on the starting space, right? But reasoning on limits at infinity.
And I have another quick question. And how is the geometry of this set, this isoperimetric set, related with M? For instance, if we, in the classic case of the Euclidean spaces, they are always balls. But here, is there something, is is it something geometrically intrinsic of the manifold that governs the boundary or something about this new set? Is it or
I would say that this question, in a certain sense, is completely open. I would say, but mostly because if I give you a random starting manifold, the limits at infinity in general are just Ricci limit spaces, right? So they are limits in the general sense that I mentioned before. So the Gromov-Hausdorff sense of a sequence of manifolds that is the same manifold but looked around different points, having a uniform lower bound on the Ricci, right? These are called the Ricci limit spaces, which in particular are RCD, okay? But the geometry of X can be, completely different from the one of M. So if you don't assume, I believe that you really have to assume strong assumptions at infinity to say how on M, to say how the eventual limit at infinity look like. Maybe the only thing that comes to my mind, if you want, I can tell you this lemma, this nice lemma. It is contained in a work appeared this year with Antonelli. This is the only thing that I can think of right now. If you assume something very strong, like non-negative sectional curvature, okay, then, and let's say that X is one of these limit at infinity, is one of these, so X is one possible limit at infinity. Then I can tell you that X splits a line. So X is splits isometrically in the following as an isometric product of R times some other space. But again, this is adding a lot of information, and here the Toponogov theorem is crucial to prove this splitting. There is also an alternative proof by Zhu, appeared, but it's quite similar, but appeared later this year, and still in the non-negative sectional curvature case, but under lower bound on the Ricci curvature and without assumptions at infinity on M. I believe that these spaces can be very, the geometry of these spaces can be unpredictable. The only thing you can study is, if you want, the regularity, but in a very metric sense, the regularity of these spaces, in the sense that you can ask yourself what are the blow-ups at any point of these spaces. And then you can estimate the dimension of the singular set, and that is different from what you can say in the general RCD case, but this is going to be technical. And in any case, it is a local information, a regularity information, not quite an information on the geometry of X. That I believe is what you were asking.
Yeah. Thank you.
Maybe I understood the question of Juan Carlos. Because he mentioned the balls. So actually,
so the geometry of the sets.
What you said in your talk is that the isoperimetric sets have constant mean curvature if Ricci is non-negative. So does this condition passes to these RCD spaces for isoperimetric sets?
This is a very good question, and the answer is more or less, because these sets are non-smooth and in a non-smooth space. And today there are some attempts of definition of mean curvature for boundaries of sets in RCD spaces, but it is something that is not quite understood. What we can prove anyway is that if a set in, for example, here in an RCD space is isoperimetric, then there exists a constant such that there exists a constant h such that this inequality holds. So basically, I don't know yet if there is a meaning, if there is a definition of constant mean curvature, but what one can prove is the consequence. So the fact that you have the upper and lower bounds on the Laplacian of the distance function on the whole space, and then you can run the argument. Then you can run the rest of the argument, right? This is actually the crucial point of our work. Yeah. And by the way, this is based, I have to say, in the RCD setting, this is based on the previous work by Mondino and Semola, where they do the same thing more or less plus a lot more for perimeter minimizer. So sets that minimize the perimeter without the constraint on the volume. They always minimize the perimeter. Then you expect them to have zero mean curvature, right? And indeed, they characterize this fact by saying that such a set satisfies this inequality with h equal to 0, right? With h equal to 0. So this is the version with h equal to constant, which is equal to constant, right? This is, yeah.
Are there any other questions? Quick question? No? If not, we finish today our second lecture by Marco Pozzetta. Thank you very much.
Thanks to all of you, and see you tomorrow.